Okay. Hi, everyone. I'm Eva Catoggio, and today I'm going to present the efficient TCAD temperature-dependent analysis of a FinFET power amplifier in large signal conditions. The most common power devices in RF applications are FinFET, MOSFET, EMT, but also new emerging technologies such as tunnel or ferroelectric FETs. In the last years, there is a growing interest for exploiting FinFET technology in the millimeter wave frequency ranges, especially with reference to 5G applications, thanks to their high cutoff frequency and their lower cost. The miniaturization of electron devices leads to a significant technological spread, the impact of parasitics, and a difficult thermal management. This one can give some self-fitting problems in static conditions or harmonic distortion in the dynamic case. In this perspective, there is the need to develop a temperature-dependent physics-based sensitivity analysis in both static and dynamic conditions. RF and microwave power devices typically used for large signal simulations require a dynamic TCAD analysis. For this reason, we have introduced a numerically efficient technique for thermal TCAD analysis through the development of an in-house two-dimensional simulator. The simulator is composed of a drift diffusion model, which includes some mobility models, the self-fitting model, and the thermionic emission model for heterostructures. These ones are strongly dependent on temperature variations. Moreover, quantum effects are taken into account through the density gradient model, whose implementation is ongoing at present. Moreover, there is in our code the harmonic balance technique, which is used for large signal simulations. In the code, the device is considered as embedded into an external lumped thermal resistance, which heat is dissipated towards a heat sink at temperature T0. The device temperature T is uniform in all the mesh nodes, and we can divide two possible cases. In the first case, we don't have a thermal resistance, and the device temperature is always equal to T0, so it is externally varied with the heatsink temperature. This case has been implemented in both DC and large signal conditions, while the second case considers a thermal resistance. Therefore, the device temperature is higher than T0 because of the heat dissipation process. The last case is implemented only in DC condition at present. Oh, just a second. Okay. Okay, with this code, we want to calculate the device response to temperature variations with respect to a cold status, which is typically 300 Kelvin. Or physical or technological parameter variations with respect to a nominal value, and finally concurrent temperature and parameter variations together. The drift diffusion code is able to perform this analysis through an incremental approach, which consists of repeated simulations at each temperature T, then repeated simulation at each parameter P, and finally, for concurrent variations, we have a total number of simulations equal to the product n times m. So this is a time-consuming procedure that can be overcome through an efficient thermal variability analysis based on the so-called Green's function approach. I present the Green's function approach starting from the temperature-dependent analysis in large signal conditions. So in this case, we have we don't have a thermal resistance, and the device temperature is a parameter that can be varied with T0. In particular, we consider small variations of temperature in order to have a linear perturbation of the device nominal working point that is, in this case, periodically time varying. So we consider the device physical models and we linearize them around the cold temperature in order to find the Green's function. This is the expression of the linearization where we can identify the local source term, which is the product between the derivative of the device physical model with respect to temperature and the delta, the temperature variation. Now we can calculate the induced perturbation at the terminal currents through a convolution integral that involves the variation sources and uses the Green's function as a kernel. This linearized approach gives an advantage over repeated temperature-dependent simulations because the Green's functions can be efficiently calculated and they need to be estimated only once at cold temperature. So we don't need repeated simulations. Now we consider a concurrent variation of a parameter, physical or technological, so we can use the previously calculated Green's functions and then calculate two convolution integrals. The first involves the variation sources with respect to temperature. The second involves the variation sources with respect to the parameter. These current variations are found considering the device in short circuit conditions, but our device has an external load. So the final delta current due to temperature and parameter variations is given by this expression. To conclude, we have a self-fitting analysis in DC conditions. So we consider a thermal resistance, and we have a temperature increase due to self-fitting that can be represented by this expression, the first expression, where we can see the final temperature device and the dissipated power. The linearization of this expression leads to a final formula that gives the terminal current calculated at the final temperature and involves the cold terminal current E0K and S, which is the thermal sensitivity. The thermal sensitivity is the delta current due to the temperature variation, which is obviously calculated using the Green's function. Our case study is a FinFET power amplifier with 45 nanometers gate length and 25 nanometers H-fin. We simulate a multi-finger device, so we have 10 fingers of 30 pins each. And we simulate a class A power amplifier with an operating frequency of 70 GHz. We have an optimum calculated, an optimum load for the fundamental frequency, and the harmonic balance technique is performed with 10 harmonics. Our aim is to validate the GF approach, varying the temperature up to 50 Kelvin and varying a parameter, which is the doping concentration in the source and drain regions of 15%. And finally, we use two different thermal resistances to see the effect of self-heating. This is the first result in DC condition with just a temperature variation. We see that the output characteristics show an excellent agreement between the Green's function solution and the reference solution. The reference solution is the one obtained through the incremental approach. And we can notice how the current is decreased due to the temperature increase above the threshold. Here we have the result of the self-heating analysis, always in DC conditions, and with two different thermal resistances. There is a reduction of the drain current, even in this case, but due to self-heating. And there is a higher reduction when the thermal resistance is bigger. The GF approach is worse in the case of the red curve, because in this case there is a stronger temperature increase. In fact, temperature reaches, it can be noticed from on the right-hand side, temperature reaches 370 Kelvin in this case. Here we have the stage temperature dependency, but in large signal conditions. So we can notice that even in this case, there is an excellent agreement, and the solution obtained with the Green's function approach is as the simulation time reduced with respect to the other one. It's about 20% of the incremental simulation, and there is a reduced swing of the dynamic load lines, which are represented in the plot. There is a reduced swing due to the effect of temperature, which produces a mobility degradation and a consequent increase of the knee voltage. Now we add a concurrent variation of the doping in the source and drain regions, and in this plot we can see the dynamic load lines, which are calculated with negligible time overhead. Moreover, doping variations further affect the parasitic resistances of the device, and we can notice that the lower is the doping, the more is the compression of the dynamic load line. Here we can go on with the power performance. On the left, there is we can notice a degradation of the output power with a temperature increase, while on the right there is the available gain, which is not only affected by the temperature increase, but also by the doping variation, especially in the compression region, so for high values of the input power. To conclude, there is the stage efficiency of the power amplifier. In particular, we have on the left, we have the drain efficiency, which is reduced by the temperature increase, but not very affected by the doping variations. On the left, we can notice the delta efficiency, And we can see that for low values of the input power, we have a higher efficiency with a lower doping, while in compression we have an opposite behavior. So to conclude, we can say that FinFET technology is promising for millimeter wave applications, and that our TCAD approach based on green functions is not only accurate but also a mature technique for the assessment of nonlinear circuits. And finally, we have validated this approach in two conditions. In these two conditions, we have seen that the drain current was strongly reduced by the temperature increase, especially with the thermal resistance, while in large signal simulations, the thermal radiation affects all the operating conditions and dominates always over the doping sensitivity. A future work can be the extension of the self-fitting analysis to the large signal conditions. Thank you for the attention.